speaker today in this session, and that is Professor Dag Breiby at the Department of Physics here at NTNU. After completing his postdoctoral training at the Grazing National Laboratory in Denmark, he joined NTNU in 2007. We has been here since then. He has authored over 60 articles in various international journals and is part of the European Union ERANET project RADOSOL, which aims to obtain a profound understanding of the nanomorphology performance relationship in active layer bends for bulk heterojunction organic solid cells. So please help me welcome Dag.
Thank you. So I will be talking about improving the performance of organic electronics by advanced X-ray studies, and of course I'm talking indirectly. Here I'm not talking about irradiation to improve the stuff, of course. First, a few words about my group. We are working on soft functional materials, polymers, organic electronics. We also work a bit with microsystems, and we have a national infrastructure, as it is called, for X-ray scattering and imaging. So we are doing materials physics. We are working with thin films, with grazing incidence studies. We are working on coherent imaging and tychography, and we also do a fair bit of X-ray physics. And what I will talk about today is in this category with thin films and tychography. So the outline is that I will first say a few words about organic electronics, then grazing incidence stuff, and finally coherent diffraction. So the organic electronics, as we have already heard about here, what already exists is this sort of commercialized, very thin screens with very high performance, and a bit more dubious. Maybe in the future one will also have commercial organic solar cells. Right? This is a test facility at DTU in Denmark from Professor Krebs' group. Yeah, I think I will just skip this one and just point to a work that I participated in exactly 10 years ago. And the reason why I have chosen this one is that I think it illustrates quite well a lot of concepts that we can study with X-rays, and also that I didn't have very much time to prepare this talk today. So it is multi-component, meaning that we are mixing things together. It's semiconducting, meaning that we have a band gap, you can say. We are talking about polymeric systems, and there is crystallization involved and percolation. So this is the cartoon way of presenting this work, which was published in Nature Materials back in 2006 with the Henning Sittinghouse's group. The tool that we are using as one of our workhorses is grazing incidence X-ray diffraction, and the way that it works is that we have a thin film on a substrate. The substrate is illustrated here, the thin film here. This is meant to illustrate an X-ray beam coming in at a shallow angle, and then in the background here you can see that we have a detector schematically illustrated, and the scattering of this film is recorded here in 2 dimensions. So how does this really work? Because as you all know, the X-rays, their hallmark is that they are highly penetrating, right? So how can we convert this into a probe which is very surface sensitive? And one way to do this is that we exploit the index of refraction, which is, you know, for glass and ordinary light, it's of the order of 1.5, and you all know Snell's law, right? But if you consider that for X-rays, the index of refraction is just a bit smaller than unity, just a little bit less than 1, then if you plug all of this into Snell's law, you will find that there is a critical angle for total reflection, external reflection. So this means that if this is your substrate, you have the film on top, and you are sending the X-rays in like this, they are refracted, and you can see that compared to what you are used to with ordinary light, it is refracted the opposite direction, right? Because the index of refraction is less than 1. So this means that there is a critical angle, and the beam is totally reflected. You get a surface-sensitive probe, even though X-rays are usually considered very penetrating, right? So by doing it this way, we have a surface-sensitive technique, and we can, with the scattering that we obtain from this thin film, obtain details about the morphology of what is going on in this thin layer. This is what one of our setups look like. We have the rotating anode source here, so this is a home laboratory setup. There is an evacuated chamber and so on, a sample chamber here, detector for alignment, and well, the key message is just that this is a rather traditional laboratory setup. And some of the very basics of X-ray diffraction that most of you presumably know is that via Bragg's law we can calculate these positions. We can use this to learn about intermolecular distances that are periodic inside of crystalline assemblies. From the peak intensities we can learn about the atomic positions, and from the peak widths we can say something about crystallite sizes. So that's the very basics. Back to this work that I mentioned in the very beginning. In a field effect transistor device, typically like this, we were using different versions of polystyrene. One has the one which is isotactic and the atactic variant of those two. And you see that, there was also a 10% amount of polyhexyl thiophene mixed into this blend. And you can see that, to our big surprise, there was more than 3 orders of magnitude change in the source drain current in this field effect transistor setup, dependent on whether we were using the isotactic or the atactic polystyrene, which came as a big surprise to us, because don't forget that the polystyrene is electrically sort of dead, right? So you cannot point directly to the polystyrene to find out what the reason is for this change in the source drain current. But if we look at this with the technique that I just described for you, looking at this with the Grazing incidence, you can see that the scattering patterns that we obtain are qualitatively different, right? And it's a rather simple exercise in this case to figure out that this is the 110, 220, and 211 polystyrene peaks, and we also see a bit of the polyhexyl thiophene, whereas in the atactic case, not surprisingly, the polystyrene is not showing any crystalline peaks, but you can see that also the signal from the polyhexyl thiophene looks very different. And an even more striking example of this was constituted in this case, where we had polyhexyl thiophene mixed with polyethylene in silane. And when we had this mixture starting up here with a diluted solution at 125 degrees, and we wanted to go down here, right? We wanted to have all the solvent evaporated and to go back to room temperature. So there turned out, well, there are 2 obvious ways to do this, right? You can consider that you either first let the solvent evaporate and then you cool down, or you just cool it down and then you let the solvent evaporate. So this means that you are going through different, so in one case you will have the polyhexyl thiophene component crystallizing first. In the other extreme case you will have the polyethylene solidizing first. But in the end you will be down here where the solvent is gone and you are left with a solid fraction of polyethylene and a solid polyhexyl thiophene. So now I hope that you are thinking, so what? And the answer to that is that this makes a dramatic difference, because if you look at what happens if you follow route number 1 here, is that you get an excellent electrical performance in terms of high mobility, whereas if you follow the other route, it does not work at all, in the sense that the mobility is very poor. This can again be understood using grazing incidence as one of the tools. So let's look first at route number 2, which is that we first cool down. So you can imagine that these reddish things here is a schematic illustration of the polyaxial thiophene polymer strands. The black one's the polyethylene, which is again a passive material, and it's in a drop of silane. So we first reduce the temperature, and you can see that the material, the polyethylene, crystallizes here. And then when we finally let the solvent evaporate, we arrive at something that schematically looks like this. And looking at the grazing incidence pattern, you can see that we have signals from polyethylene here, which is fully isotropic, meaning that the polyethylene crystallized here are randomly oriented. There is no signal from the polyaxial thiophene because the polyaxial thiophene has not been able to crystallize. Following the other route, the polyaxial thiophene will crystallize first, and then when the polyethylene crystallizes, it will be kind of squeezed away, and it turns out that this leads to vertical stratification, that the polyethylene is anisotropic, same with the polyaxial thiophene, and again we have evidence for this in the signature from the grazing incidence studies. So this was one example. It was published in Nature Materials in 2006. We have also been involved in a range of other articles where grazing incidence has been used. For example, recently with a group in Belgium, where we have been looking at differences in homocoupling. That was a bit of traditional X-ray studies. I will go on to a bit more modern approaches, and that takes us to the synchrotron here in Grenoble, the European Synchrotron Radiation Facility. What happens inside such a ring, which is almost 1 kilometer in diameter here, is that we have electrons orbiting at essentially the speed of light, and whenever they are forced to go through a magnetic grid structure like this, they will be accelerated and X-rays are emitted tangentially. These X-rays can be used for materials studies. So just briefly, one example of work that we are currently involved in on mesoporous materials. They can, for example, be silicas, and they can, for example, be hexagonal, like the structure that is illustrated here, but they can also have, for example, FCC structures. And what I'm showing you here is a mixture of a silica precursor together with a surfactant and water and ethanol. And what happens is that this ethanol gradually evaporates, and as a function of time, you can see that this diffraction pattern entirely changes, right? So at the start, you see that there is no signal. Then suddenly, when this ring appears, this means that we have passed the critical micelle concentration. And then eventually you see something forming here. This is the signature of hexagonal tubuli of micelles forming inside of this solution. And you can see that this gradually grows over into a structure which has a very highly developed three-dimensional diffraction pattern, right? And the reason why I put this arrow here is to highlight that this peak coming up here, first in the hexagonal structure, it stays put during the whole sequence, right? And the first interpretation that we had of that was that this was a coexistence between two phases. You know that we have some kind of three-dimensional structure here coexisting together with this hexagonal structure. But we have looked more carefully at it, and it turns out that this that the correct interpretation is that this peak becomes an integral part of the arising three-dimensional structure. So what we are really talking about here is a topotactic phase transition, meaning that the cylindrical micelles that we have initially are forming some kind of a template for the three-dimensional pore structure that comes up later. So to further emphasize this, this is the last stage of the diffraction pattern that I showed you, and here is a simulation that we have made where you can see that we are capturing all the main diffraction features, giving us full confidence that this is correct structure. Just to further emphasize this, I'm zooming in here. And here is a cartoon version of what we believe is going on. So first we have these cylindrical micelles that are in this case seen along their long axis, oriented with respect to a substrate, as you see here. Then they start to curl up a little bit. So this is a perspective drawing. We just see them from a slightly different angle. And the difference between what I have shown in red and gray here is just meant to illustrate that these are in different symmetric positions in the final structure. So these gradually curve up and break into smaller units, and it turns out that in the very end it can be described by the so-called Wery-Phelan structure that some of you have maybe heard about. It relates to the Kelvin problem of how you can partition space into equally sized units with the least border area, right? And what is also worth noting here is that this has a very particular orientation with respect to the substrate. It's a 2-1-1 orientation, but this is then fully consistent with the simulations that I just showed you, that the contraction is really taking place along these original cylindrical micelles. The final part of my talk deals with coherent diffractive imaging, and my rhetoric question is then first, is there a need for a new imaging technique? So for example, for bulk heterojunction solar cells, the organic material is, as you know, delicate, low contrast, and the length scales we are talking about are of interest are typically 5 to 500 nanometers. So existing imaging techniques includes SEM, perhaps with the focused ion beam, and also transmission electron microscopy in 2 or 3 dimensions. Drawbacks of these techniques is that they are invasive, destructive, they require ultra-high vacuum, the sample preparation is difficult, and what about doing in situ studies using these techniques? That's next to impossible in most cases. Before I proceed, I'll have to just give you a cartoon version also of what is coherence, right? Because that's key to understand the next concepts that I will be talking about. So coherence relates to waves, and for the light to be coherent, we cannot have different colors like here. The light has to be highly coherent and with well-defined phase relations, right? So this is schematically indicated here. Lasers are the key example of this in daily life. And the clue with coherence is that it gives you stationary interference patterns and also speckles. So if you look at a typical diffraction pattern that we have from one of our systems, if you look closely, you will see that there is a well-defined speckle structure in these images. So how is this used for imaging? Well, one use such a beam of coherent X-rays, and to find this you have to go to specialized synchrotron beam lines. This coherent X-ray field is shown onto the substrate, onto the object, and then whereas in a traditional imaging setup you would have had an objective lens here so that you would get an image on your detector, right? But in the coherent diffraction technique, instead of detecting the image, we are detecting the scattering patterns, and then using a set of iterative numerical techniques, one can actually, from a set of diffraction patterns, calculate what the object looks like with to high resolution. So the first example that I want to show you of in this regard has to do with the in situ wetting of silk fibers. And the wetting of silk fibers has been known for millennia, right? Probably that if you expose silk to water, the water will be absorbed by the silk fiber and it will expand. But to the best of my knowledge, nobody else has looked at this in situ before. So the way that we set out to do this was that we designed a holder like this and mounted a single silk fiber across here. This was then put into an enclosure, like you can see here. And these, here we have one window and here another window on the back side. The coherent X-ray beam is coming in here. And as I told you, the silk fiber is inside of this enclosure, which is used in such a way that we can measure the X-ray signal coming out on the other side. And of course we can vary the humidity then inside of this enclosure. So here is one example of a cross-section that we get. So this is numerically reconstructed from a range of scattering patterns. And you can see the well-known facets of silk here. And inside you can see that there are all these small features that are pores inside of the silk fiber. Another way of viewing this is shown here in 3D, where you can clearly see that these pores inside of the silk fiber are features that are running parallel to the long axis of the silk fiber, right? So we measured this first in a dry state at the relative humidity of less than 5%. And then we measured it again in the wet state, meaning that the relative humidity was close to 100%. And indeed you can see that the silk fiber has expanded like you would expect. But in addition, with this technique we are able to look inside the fiber while this is happening, right? So you can see that, and again to our slight surprise, we could see that these porous features that we saw inside the fiber here remain intact at the same places, which is evidence that that the water which has been absorbed by the silk fiber doesn't go into those pores, as you would maybe intuitively have guessed in the first place, right? It rather goes into the hydrophilic silk proteins that are known to constitute the rest of the fiber here, right? So it's quite cute, I think, that we can see this in situ and non-destructively, and of course it opens for studies of various ways of looking into materials and to see the effects of liquids permeating into materials and whatnot, right? And a nice feature of this is also that this coherent imaging technique is quantitative, meaning that we can extract the electron density distributions. And then you see that, so these are histograms. Basically, the black one is the before, I mean in the dry state, the blue one is in the wet state, and you can see that the number of voxels containing air goes down, of course, because the silk fiber swells, and you can see that here the difference in electron density between water and silk is very low. So if the water had gone into the pores, we would also have, as I said, that would have meant that the appearance of the previous here, these would have appeared reddish afterwards, right? My second example is in collaboration again with a group at DTU, Krebs group, and Andreasen. It's an organic photovoltaic tandem cell, where you can see that there is a silver electrode, P.PSS, blah blah blah, P.P3HT, etc. It's a tandem cell, so it has two layers. But what I want to ask you then is, how do you check the quality of these layers? How do you look at this? Because you know, these layers are not going to be perfect, as you all know. They are going to have irregularities and so on. So what we have here is a technique that we can use to actually look at these layers. So here is what we got. What we did was that we had a stack like this. We used a fib to focused ion beam to cut this into a prism-shaped thing, like you can see here. These cuts are artificially made numerically afterwards, but you can clearly see that we are able to distinguish these different layers, right? And one nice thing about that was also that we were able to identify short circuits here, which explains why the performance of this particular solar cell was quite poor. I don't have the numbers here, but this was also repeated with a different stack where additional efforts were made to avoid this kind of short circuits between across insulating layers that is shown here. So I refer you to the original publication. I just want to emphasize again that for these different layers we can get quite good estimates of the thickness and the quality of the different layers, right? That's the main take-home message from this slide. Last and final example that I will also go through very quickly is that in collaboration with a group in Belgium, we have been looking at fast scanning calorimetry, and this is a chip for fast scanning calorimetry. Again, so these are electrical contacts and so on. There are thermocouples and so on this chip. Here we have a small silicon nitride window, meaning that when we are sending, which is transparent to X-rays, which means that when we are sending the X-rays towards this area, we can look at the diffraction pattern on the backside and again see what is taking place here. And what is fantastic about these fast scanning calorimetry chips is that people using them claim that they can have temperature changes of 30,000 Kelvin per second, and this is owing to the very low thermal mass that you have in these cases, right? It's just a very, very, very small sample, which can then be heated and cooled extremely quickly. So here's again a close-up of what is going on, that we have the silicon nitride window with the organic film deposited on top of it, and by shifting the sample around, we can look at the structures that we see on this silicon nitride window. And by doing this, we can see then that the co-continuous network in P3HT PCBM, which was the standard sample that we looked at here, how these co-continuous networks form. Right, that in the first case it was just quenched from the melt, which can be done very quickly with this setup that I just described to you. And one can then, after various annealing times, look directly into how the morphology has developed as a function of annealing time. Yeah, we have also been doing a bit of nanomechanics with squeezing balls using this setup, but that I will not go further into today because my time is out. So in conclusion, I think that organic electronics cannot be realized without understanding morphology. And I would also emphasize that grazing incidence X-ray scattering has become the tool for studying thin film polymer morphologies. And then in the last part of my talk, I was talking about coherent diffractive imaging, which has a resolution currently down to tens of nanometers. It is quantitative and high contrast, and it can be used also for in situ studies. So finally, the acknowledgments that goes to people here at the NTNU that we are working together with. I should in particular mention Nilesh, who is in the audience and who has been heavily involved in the recent activities. Some excellent international contacts that we have had a lot of collaboration with during the years. And then third column here is on X-ray collaborations. The second column was in organic electronics, right? Okay, with that I thank you for your attention.
Okay, then we open up for questions.
I'll just be loud.
No, that's okay.
Okay, thank you. Thank you very much. That was amazing. Also, that new technique, I'd never seen that, so I think that's very amazing. The question is it's about this new imaging technique. What chemical information can you get from it? So does it compensate? Can you tell crystallinity, or so what can you? The graphs you saw, what can you take away from that?
Yeah, let me think how to answer this. I mean, it is in some sense a high-resolution microscope, right? And in addition to that, what goes beyond the light microscope is that the resolution is better, and that you can obtain images in 3 dimensions. And also the possibility of doing in situ work. And finally, that well, not finally, but one more important point is that the information is quantitative. I mean, the contrast is quantitative, so that you can relate this to the electronic density. And this efforts are underway also to be measuring at a set of different wavelengths, and when one can do that across an absorption edge, for example, then one can hopefully also in the future have some chemical specificity. I mean, what elements that are involved, right? Yeah.
Yeah, my question is sort of following the same line. Is there any perspective to actually get it down to atomic resolution at some point?
Of course, that's the dream of many people, and efforts are being made to do that. The problem, the showstopper, so to speak, is that is beam damage, radiation damage. So in order to, to increase the resolution by a factor 2, you typically have to increase the dose by a factor 2 to the 4th power. Right, so you cannot do this very many times before it gets prohibitive in terms of radiation damage. But people are also finding ways of circumventing this, so that if you are able to prepare a series of identical copies of your material, then one can in the future use the so-called free electron lasers that are coming up in Stanford and Hamburg and other places, where one is doing single-shot diffraction experiments, meaning that you expose your sample to one shot, and then the sample is gone, it's burnt away, but just in the fraction of a second before the sample disintegrates, you have already gotten the diffraction signal that you need, right? So this is a way that people are already people have already published some works on the dynamics of I think some membrane proteins studied using this technique. Yep.
Other questions? Okay, then we thank the speaker again.